Okay, so good morning, ladies and gentlemen. I think we have to start our conference. Well, despite that, at least 98% here Russian speaking, but at least one plenary speaker is English speaking, so that's why we need to talk in English, of course, because it's English speaking conference. Okay, well, dear colleagues, challenging times, and I'm sure that many of you remember the last conference, which was in the 2021. We did it fully online, and it was a good tradition. Actually, we launched that conference that we associate the conference with slogan. And this time is slogan of the conference, is the motto of the conference, Artificial Intelligence Expanding Horizons. Today, the discussion of artificial intelligence and machine learning methods has gone far beyond the scientific community. In social networks, bloggers with a very modest knowledge of and understanding of mathematical methods in pursuit of views and likes. So they're trying to explain how to use ChatGPT, DALL-E, and other networks just to generate an image, compose a text, and even to generate a code. But computer science actually is constantly pushing the horizons of the use of machines in society and providing unprecedented, progress in many areas. And we can't avoid the work of the metaverse. And the metaverse in artificial intelligence, now we call Intelliverse. And progress in AI systems often seems to be cyclical. And now we are coming to the next cycle, the cycle of development of generative neural networks. But as usual, over the last 30 years in our conference, we will discuss appropriate and discuss classical pattern recognition as always. But also this time we will focus also on neural networks because it's in hype, it is in progress, it is the modern state of the art, and find and evaluate modern results in the field of AI in Belarus and what will be happening in this building and during the conference. My name is Alexey Belosarkovsky, and on behalf of organizing committee, I would like kindly to give applause to our openers, those who organize the conference and those who open the open session. So please give applause to our chairman, Professor Alexander Nedved, academician of National Academy of Sciences of Belarus, Professor Sergey Ablameyko, co-chairman of the conference. Okay, again, co-chairman of the conference, Professor Alexander Tuzikov. And special applause, special thanks to our host, Dr. Yuri Orlovich, Dean of Faculty of Applied Mathematics and Computer Science, BSU. So, Mr. Chairman, now you have a floor, please. You can hold the session, the open.
Maybe. Okay. Thank you for your attention. First of all, I'm very glad to see everyone and our conference now collect about 72 presenters from 11 countries, and of course I think that we can start our conference. And now I'd like invite to this place our Dean Yuri Orlovich, because this conference supported by Faculty Applied Mathematics and Computer Science, our university. Юрий Леонидович, тогда пару слов.
уже столько лет данная конференция проходит у нас в Республике Беларусь. Сначала это была конференция по распознаванию образов, анализу изображения, наверное, и сейчас она конференция по распознаванию образов, работы информации. Мне кажется, что тот вектор, который вот задан был в те далекие годы, он достиг своего такого значимого результата, потому что традиции конференции крепились, статус сохранился, география расширяется, появляются новые части конференции. Ну и хотелось бы пожелать всем в рамках, которые пройдут в рамках конференции, плодотворной работы, эффективного взаимодействия и конструктивного диалога. Поздравляю всех с открытием конференции.
Okay. As our colleagues mentioned, we started in 1991, and I will speak a little bit later. I will show you all history of this conference, and it's great pleasure again that in spite of all troubles, difficulties, and so on and so on, we passed these 30 years, and of course I wish success of this 16th conference and of course for next future conferences. Thank you people who submitted papers, who come here, and we will have fruitful 3 days. Thank you.
Other person, very important person of our conference, it is Professor Alexander Vassilievich Tuzikov. He is he from United Institute of Informatic Problem, and it's other organization, very important organization that support our conference, and of course I invite him to this microphone.
Thank you very much, dear colleagues. I'm also very glad to say a couple of words. Also, I'm not here in the program, but we also like were the organizers of this conference, and also you know that this conference is biennially organized, and organized once in the United Institute of Informatics Problems of the Academy of Sciences, once in Belarusian State University, and once in Belarusian State University of Radio Electronic and Bioinformatics. So the previous conference was organized in Academy of Sciences, and it was still online conference. And also it was organized also very good. Alexei Belotserkovsky was the main organizer of this conference, but it was online. And this conference is like in as I understood it, hybrid mode, right? But mostly we have offline presentation, and it is great that after pandemic we have such an opportunity to meet again and to discuss the interesting directions. And I must say that there are one direction which is now dominated in this area of pattern recognition and information processing. I mean, this artificial intelligence technologies and various deep learning architectures which are applied for various problems. And as I've seen, and you also see from the program of the conference, we have a lot of reports which are devoted to this subject. So I'm also very happy that we have today this conference. It is the main conference in Belarus on this topic of pattern recognition and information processing, and it's great that organizers of this conference did a big job of doing everything to have us here and to prepare the conference proceedings also as well. So I would like and I hope that the conference will be very interesting and will have like the place where we can meet, discuss, and see also new results and novel directions to work. Okay, thank you very much.
Thank you very much. And now I'd like say a few words from me because we spent very hard work for preparing of this conference, and now maybe we have very good collaboration with different organizations because, of course, big work was produced from team of Belarusian State University, but also we take help from United from Academy of Science, Institute of Problem of Informatics, and I'd like thanks every person of our local committee, also for Victor Kazachonok, Professor Victor Kazachonok, who helped me, Alexei Belotsarkovsky from Academy of Science, and Marina Lukashevich too. And also, I'd like special thanks for our program committee that will supported by our persons that sitting near me. Thank you very much. And now I think that I can open this conference, and I propose open this conference, and we can start. Thank you.
we published, we still have, because we slowly moved to the two languages. I will show you later on, because 91, 93 we had Russian language, and from 95 we started to use two languages, Russian and English languages, and this is also good. In 97 we first time we received auspicious of the International Association for Pattern Recognition, and it became really fully international conference. Леша, что-то у меня не двигается. Посмотри. Нормально. Well, and that's I put all of these conferences you can see in these slides. So 15 conferences for 30 years, and you can see here how we moved from one Russian language to Russian English. English, it was up to 1997. From 2001, we had one English language. And as my colleagues also mentioned, three main organizations are responsible for organizing this conference. This is Belarusian State University, Belarusian State University of Informatics and Radioelectronics, and the United Institute of Informatics Problems of National Academy of Sciences. Before 2002, it was called the Institute of Engineering Cybernetics. And a group of scientists from these three organizations, you can see we successfully passed all these 30 years. And this is what really good. And you can see a number of countries was quite a big, about 10, 15, even 30 countries in 2009. About 100 papers usually we have every year, so it was not bad. And this year, we have 16 PRIP conference. You can see it's also 72 papers from 11 countries, and Belarusian State University, and Professor Nedved is the chairman of this conference. So because I would say that we had these problems, we thought last year, especially to move to the 16 conference, because situation is really quite difficult, because flights do not fly, relations with Europe and America is not good, and we did understand that we will not have much pupils from Europe or from America. But anyway, we decided to do it. And the hybrid mode, because in 2021, we had online conference organized by the United Institute of Informatics Problems, and Professor Tuzikov mentions that Alexey Belotyrkovsky did a big job. In that time, it was very, very good organized online conference. But now we can move a little bit between countries. Flights started to fly, and we decided to have a hybrid mode, online and offline. Well, you can see I put several photos here from different conferences, because as I told you, we all usually have several volumes even of the conferences, and we are happy that last three conferences we published by Springer book. It was also very, very good. And today also, you know, that we already published proceedings of our 16th conferences, and this is a great thanks to Professor Kazachonok, who did this collection of papers published online. It means that electronic form, but we will see in the future. And of course, our also partner, this is a Journal of Pattern Recognition Image Analysis from Russian Academy of Sciences, and many, many years, I would say that after the conferences, we have a collection of best papers published in the Journal of Pattern Recognition Image Analysis. I would say special thanks to Dr. Igor Gurevich for supporting all these 30 years, I would say, supporting our conference. And we also have agreement with journal this year, and we plan after the conference in October, November to select the best, let's say 10, 15 papers, and we have agreement with this journal, and we will submit before end of this year. We will submit, as I told you, 10-15 conference to this journal for special issue selected papers from PRIP conferences, and this is very big support of our Russian colleagues, Russian Association for Image Analysis. We have very good relations with them, and this is good support, as I told you, for our Belarusian studies. And this journal is very famous in the world. He is in most of the databases, including, of course, Scopus and many others. And this is very good support of our conferences. Some photos you can see here. In 2009, was a big conference in Belarusian State University. Last year it was, as I told you, virtual conference. It's really it was nice event. As I mentioned, PRIP organized by 3 organizations, 2 universities and United Institute of Informatics Problems of the National Academy of Sciences. Conference was supported by IPR, in the past, IEEE and IEEE, Computer Society, INTAS, Belarusian, different funds, Fund of Fundamental Research, Fund of Informatization, Ministry of Education, National Academy of Sciences in different times. So we are really grateful to our sponsors for supporting our conferences. And now PRIP is generally well known and generally recognized in the scientific world, is one of the leading international conference in image analysis pattern recognition in Central and Eastern Europe, and so on and so forth. And as I told you, papers from this conference published in the Journal of Pattern Recognition Image Analysis and in Springer lecture notes in computer science. Well, it's put in Russian slide. I did not translate it because we have a very strong groups here in the United Institute of Informatics Problems, first of all, under leadership of Professor Tuzikov, Dudkin. Unfortunately, Alexander Sench passed away. I will show you. Zalesky, Kovalev, Vassili, Valery, Vassili, Starovoitov, Bguir, Belarusian State University Informatics, Radio Electronics, Tatur, Цветков, Лукашевич, БГУ, Краснопрошин, Медведь, Харин, Ablameyko, Polotski Государственный университет. So many groups work in this area in Belarus, and this is very pleasure and very good. Unfortunately, some of our friends left us. Вы видите, ушли из жизни люди, с которыми мы начинали. Профессор Семашко, Рауф Хасрович Садыхов, Николай Николаевич Парамонов, самый наш учитель Вячеслав Сергеевич Танаев, кто поддерживал всегда нас, тоже ушел из жизни. Александр Арсеньевич Дудкин совсем недавно, к сожалению, тоже покинул нас. Мы будем помнить этих людей всегда. Well, in the conclusion, I would say great thanks to Russian scientists, first of all. This is Igor Gurevich, for his enormous work. To more than 30 years he supported us. Of course, Professor Zhuravlev, he was scientific leader for all this period. We had great support from Italian scientists, from Swedish scientists, English Maria Petrov supported us also. She passed away some time ago. This is our international friends. They really support our conference. And of course, great gratitude to all people who contributed to development of these 30 years, for these groups, for conferences, and let's hope that we will continue to do it in next 30 years. Thank you very much. Probably if you have some questions, I will be happy to answer in English, in Russian, in any language. Если у кого какие вопросы, то... Нет, в этом году мы пробовали, но не получается. Виктор Владимирович старался, писали, мы пробовали. Марина, пока не достигли мы никакой договоренности. Да, все официально написали в журнал, официально Гуревич ответил, они ждут порядка 10-15 статей до конца года, мы должны им отправить. будет в следующем году специальный выпуск журнала PRIA, посвященный PRIP нашей конференции. То есть эту договоренность мы с Алексеем Михайловичем переписывались официально, и все, есть письмо, все. Они ждут до конца года, поэтому нам надо будет отобрать 10-15 статей, значит, вот из наших 72 представленных здесь. И статьи, понятно, чтобы тоже все авторы слышали, что расширенные статьи – это не доклад на конференцию, это 4-5 страничек, это если кто пожелает, вот я еще раз скажу, быть опубликованным в журнале PRIA, Pattern Recognition Image Analysis, то мы приветствуем, но мы должны понимать, что это большая, хорошая журнальная статья должна быть, потому что это не годится простое там расширение с докладов маленькое, то есть это надо делать хорошие статьи, но мы надеемся, что так 10-15, по крайней мере, пока с Алексеем Михайловичем мы переговоры вели, желающих много, но я говорю еще раз, мы будем отбирать, потому что, в принципе, должны быть хорошие статьи, это, чтобы все слышали, тоже все понимали, поэтому, а журнал этот известный, я говорю еще раз, он входит во все базы данных, и, в принципе, не так легко туда, честно говоря, попасть. Еще, коллеги, какие вопросы? Да. Я такого не слышал, Вася не видел. Все в Скопусе, все пока, все везде, все хорошо. Тут надо смотреть, наша ситуация меняется, но насколько пока я вижу, все российские журналы, все там все остаются. Которые были в Скопусе, все остаются. Поэтому, это, говорю, вопрос такой у нас сложный. Но по PRIA это точно ничего не слышно, не было вообще. Потому что мы с Гуревичем все время на связи. И сейчас готовится в PRIA, готовится специальный выпуск большой по всем школам, там, СНГ, скажем, за там много лет, особенно за советский период. И я там писал был тоже про наши такие в общем, такую одну общую статью про всех вас, скажем так. Потому что мы думали, когда обсуждали там год назад, два. У нас был, вспомните, специальный выпуск года 2 назад, когда белорусские мы показали школы. И мы уже не стали по новой писать, а я такую одну написал про всех, и все, и она пошла. Но там, конечно, сейчас немножко жалко, потому что украинцев не будет, там будут только русские, мы и армяне, по-моему, в этом журнале. Но русские, потому что я редактор этого выпуска тоже вместе с Гуревичем, и через меня все статьи проходили россиян. Их много, они интересные, они показывают всю историю там, института проблем передачи информации, например, там, или там других каких. То есть, большой очень такой выпуск готовится в начале года, я думаю, если это еще выйдет, это все. Поэтому, Но с этим журналом хорошее сотрудничество, все это. А по российским журналам у вас здесь как решения там какие-то общие будут приниматься. Там, пока все, мне кажется, я вижу журналы, по крайней мере, в Скопусе все отражаются. Большинства, по крайней мере. Я могу говорить за все, но там, где я публикуюсь, пока все нормально идет. Коллеги, еще какие вопросы, мысли? Нет. Спасибо большое. So we move to the second presentation. As chairman of the Plenary Session, I give a floor Anna Gavrovska, Andreja Samčović, Dragi Đuković, Serbia, no reference perception, basic image quality evaluation analysis using Approximate Entropy. Mm-hmm.
Co-author of this paper, together with Dr. Anna Gavrovska and Dragi Đuković, and we all are from the University of Belgrade.
So do you hear me now? Okay, sorry. So Serbia, as we know, is one of the Southeast European country here. And Belgrade is actually the capital of Serbia, which has approximately 2 million inhabitants, I think, like Minsk. So this Belgrade University is the public one, and it is actually the general university It is not the technical university which you have here in Minsk, but it covers of subjects like medicine, technical sciences, philosophy, then natural sciences like mathematics, and so on. It's relatively, I could say, big university with more than 80,000 students. So I actually come from the Faculty of Transport and Traffic Engineering, and my colleagues from the Faculty of Electrical Engineering. So in this presentation, we actually tried to explore actually one quality measure for the assessment of the images. So there are nowadays, I would say, a few the quality measures for the assessment of image quality, and the great division is on the subjective and objective quality measures. So nowadays we have millions of images which are downloaded each day. As we know, approximately we are all on the social networks every day, like Facebook, like Instagram. We download images we have on YouTube, for instance, or other platforms for signal streaming. So I would say that for the objective quality assessment methods, we have full reference, reduced reference when we have a reduction of some image details, and also no reference quality assessment methods. I would say that today the most important is no reference quality assessment measure, because we don't know actually the source of the images which are downloaded. We see, for instance, the images on Instagram, on some other platforms, but we don't know the original, how the original images look like. We know how they look like when we download those images, but we don't know the original. So that means that we have no reference method. So actually, these methods are distortion related and without any knowledge about existing distortions, because those images, as we know, have distortions. Today, in last 10 years, a dozen of quality methods are developed. I would say earlier these quality measures were only few, but now we have approximately 50 quality measures, and the number of these measures has been growing in the last years. So I would say that we have models which are very popular, such as Nike, Brisk, and Pike. In this paper, we took an emphasis on Pike, which means perception-based image quality evaluation. Why Pike? Because Pike is very good for some methods we want to have details, such as, for instance, medical images, because in medical images, all details are very important because of diagnosis, as well as the images from drones, that means unmanned aerial vehicle. And the images taken from drones are very important today because they have a lot of details. So the statistical naturalness includes some properties of human visual system. As we know, there are some approximations of this model, but actual actual model has not been yet included of human visual system. And actually, I would like to say that in our paper, we used so-called live data set. This database is publicly available. And also, there are several distortion types. In our research, we used to include the compressions with the JPEG, Joint Photographic Expert Group, which is still nowadays the most used compression on internet, although it is nowadays more than 30 years old. And we don't see any other kind of compression which should change JPEG. My opinion is that because the industry is interested to use JPEG compression more and not to develop other types of compression. Then we have JPEG 2000, which was developed in year 2000, but nowadays it did not replace JPEG. It has limited purposes. Then we used white noise, Gaussian blur, and fast fading, which is used in channel coding. So here we have so-called difference mean opinion score, DMOS, for distortion which we used. We know Shannon entropy as the quality measure. This is very old type of measure, and but very much used in the information theory and also in the signal processing community. Shannon entropy is very old measure. It comes from the pioneer work of Claude Shannon from the late 40s years, 1949, when he published his pioneer works. So this, on the right side, we have quadratic and linear models, which is used to compare these three non-reference models. Beside the entropy, there are several other types developed in the measurements, such as so-called approximate entropy. This approximate entropy is also mathematically can be calculated, and it was developed in the last 10 years, and it found its applications, for instance, in the contour segmentation or evaluation of bio-movements. So I would like to emphasize that the quality assessment of images, which doesn't require reference, that means no reference image method, is nowadays not an easy task, because actually we don't know in these methods the source of these images. I would like to say that in this method, the image is first pre-processed. So we have the phase of pre-processing, because we should prepare after this pre-processing phase. We have coefficients which are then easily can be processed. Those coefficients are mean subtracted and contrast normalized coefficients. I would like to tell that it is similar with, for instance, image transforms, such as discrete cosine transform, when we have also the phase of pre-processing, and then we have transformed coefficients which are then easily to make some processing methods. So here we have a pike index, which is mathematically tractable, and this is very easy from the machine to calculate this index and then to use in the image assessment. So actually we have a difference mean opinion square, which can be with 0 or 1, and also it can use the values between 0 and 1. That means when this value is 0, then we don't have distance between original and processed image, and that means we have the image which is almost the same as original image. And high values of difference MOS means that the analyzed image has a relatively poor image quality. So in this comparison, we would like to make the correlation between these measures, and the very old measure for the correlation are so-called Pearson correlation coefficients, but it is still used, although it is very old measure for the correlation. I would like to emphasize that pike method is very good for extracting local features, and these local features, for instance, is very important in the medical image, as I previously told, because we want to make clear difference to make the proper diagnosis when we have this medical image, or when we have the images taken from the drone. In this experiment, we used about 30 reference images taken from this live database to make comparisons between these quality measures. So here we have a very well known formula for Shannon entropy, and I will not go into details because almost everybody from the signal processing community knows this very simple formula. This approximate entropy is actually the different measure when we compare to Shannon entropy, but it is more precise, I would like to emphasize, in the measurements. So here we can find the formula for the approximate entropy. So it is also mathematically tractable as Shannon entropy. When here we have the dimension m and also the radius r. And also we have here some constants. So actually for each image from this image live database, we calculated Shannon entropy, approximate entropy, and pike index according to the formulas which are mentioned in the slides before. So they can be easily calculated by some machines. So here we have two common measures for the correlation. Beside Pearson linear correlation coefficient, we have also Spearman correlation coefficient. So in this diagram, we have an input image. So in this branch, we have to calculate a Pike index. And here in this second branch below, we have to estimate approximate entropy. And then we have to calculate this quality value by comparison Pike index and approximate entropy. So in the simulation results, I would like that we calculated so-called scatter diagrams. And in the scatter diagrams, we have a Pike index and also this difference mean opinion square. So here in this right side up, we have actually the higher concentration of points in this scatter diagram. We calculated also the correlations for different kind of distortions. So here are JPEG 2000, JPEG, white noise, Gaussian blur, and also phased fading. What is interesting to see, we can see that this value of the coefficients is the highest for white noise, and the lowest correlation we can see for fast fading distortion, which is interesting to observe. So here we have a JPEG distorted input image, and then we have calculated Shannon entropy, approximate entropy, and Pike index. Some correlation results per distortion is calculated by using low approximate entropy. So we can see then again the best results are obtained with white noise, which is also interesting to observe. So actually, I would like to say that this proposed framework, by including approximate entropy in the calculation of Pike index, is very good to improve the correlation results from the different kinds of distortions. And to conclude this presentation, I would like to tell that according to our knowledge, this is the first time for including approximate entropy in the calculation of this no reference Pike method. And we can see some very interesting issues, like, for instance, the application in the local feature estimation, and actually some future research concerning this image quality assessment can be done for the different types of distortions, because we used only these 5 types of distortions, and we know that also there are some other types of distortions, and also for the different with images with the different level of details. For instance, the images with a low level of details, with moderate level of details, and also for the images with very high level of details, which is also very interesting for us as users to assess the quality of images As we know that every day we have the connection with downloaded and as well as uploaded images on our social network accounts and also for the image streaming. Thank you.
Thank you very much. First, I would like to thank you that you come to Minsk and to participate in our conference. And the second one, I would like to ask you finally, what are your conclusions? Which quality measure you consider like from those which you compare with the best one?
So I would like to say that it depends on the type of images. As we know today that we have almost 50 the quality measures, and in our research we want to show that this quality measure is good for the images with very local features, such as, for instance, medical images and drone images, because we don't want to have a big distortion for this type of images. For instance, for the images when this type of distortion is not so important, for instance, for the images taken from some streaming platforms, or social networks, it is not so important. And in those cases, we can use the other quality measures. For instance, for Instagram, it is not important to have very low distortion.
Finally, for your purposes, for your kind of images with some importance of detailed information, which quality measure do you recommend based on your research? Just to say, this is our personal entropy, for this special topic of interest, the best one from those which we compare. What you can say now?
Well, I cannot say, but I would like to say that this approximate entropy is relatively new quality measure. So I think that a lot of research should be done in the future. We know that this Shannon entropy is very old quality measure. I think that the best characteristic of the Shannon entropy is the similarity. So when we want to have to make a quick the estimation, I would recommend this very old quality measure. But when we want to have more sophisticated research, we should use approximate entropy.
So you did your comparison based on this live database and using distortions, right? Yes, and when you did your conclusion based on this comparison, but when you do not have a reference image, so you can use your quality measure value, and which quality value is good and which is bad. What is this threshold when we say, okay, that 0.86 is a good, for example, value, or it is a bad one for quality?
I think that all coefficients higher than 0.9 are relatively acceptable, but lower correlation coefficients are not so good, according to our experience.
More questions? No, that's good.
Is there a way to create a universal
My opinion that we will not have the universal quality measure because the researchers must have to research, you know, as I mean. When the researchers have the only one universal quality measure, then they will not make researches, but they must do it in order to improve their results. So I think the trend is to develop more and more quality measures, because I'm really impressed, because now we have almost 50 quality measures, which was not the case, for instance, 10 years ago.
Right now we have thousands of image compression algorithms, right? But we still use old ones. It does not welcome new methods. So what do you think? Is it better to keep sparsing these methods and use only not wide, but narrow directions, or create something, maybe combine and create a system that evaluates which methods to apply?
As I understand, researchers should make research on different algorithms, and they should make a pressure on the industry to include their methods. As we remember, for JPEG 2000, the pressure of researchers is to apply wavelets. But after that, the industry didn't want to include those algorithms. But as we know, those algorithms are still being developed. So we have these two waves, I would say, the industry and the research way. You're welcome.
So we are talking about perceptual quality of images. So I know some photographers who is very proud about that, and they use a very advanced method for deep noises, etc. But they finally refuse to use them because they're making images that are not alive, photographs. So people refuse to get this filter kind of filters, which is formally improving the quality in terms of all the criteria, formal criteria. So the beauty and the mathematics is still legitimate. That's one point. Another point is that despite classical method is just to investigate the image and distribution of noise, and then to make something to denoise. But recently, when, for instance, generative networks doing artificial images, and they need to increase the resolution, what is certainly involves certain distortion, they don't use these approaches, mathematical. They're using autoencoders and neural networks which do it better. So can you comment on this?
I didn't think about that, but as you emphasized, the perception is different. When we use, for instance, these kinds of make the photographs better as they are actually. And you told actually that it depends on our perception, how we percept, for instance, the natural images and the images by using some methods like Photoshop, I think, as I understand you. So our perception is actually different. For all of us, make different perceptions, as I understand what you want to say. And also there is difference between natural image and computer animated images. And so in this research, we took into account natural images.
Okay, no questions? No questions. Thank you very much again. Okay, we finished the first hour session, let's say, of plenary session. Now we have 15 minutes break.
Okay, focus okay.
Thank you. So, is it still good morning? Good morning, ladies and gentlemen. So, my name is Vassili, and I'm going to give this presentation. And what I stress, underline that this is the topic of my very particular presentation, very particular paper. I mean, in the program. But then I decide, once I was invited to give a plenary talk, then I think it would be interesting to give a more broad presentation what we are doing. So mostly I will be speaking on what we are doing, what my group doing, what my students doing together, and something else. So you see the title, the efficiency and security problems in this so-called artificial intelligence era. And on the bottom, you see the website, which is totally informal, but nevertheless, I invite you to visit that site and to see something what we develop and what could be interesting for you, etc. This is not just website with text and pictures. It's something computational services are behind that. So that's really working in real time. Okay, so the content. First, I would like to introduce what we are in general doing, and we are doing medical image analysis, classification, generation, etc., etc. And then the second part is an approach to the problem of security of our work, and this is a very important point which attract more and more attention. And of course, some people who doing this law
law, introducing new law, new limitations, etc., etc. So they are working, and they put more and more limitations for our work, which is by law, not by ethical, aesthetical, and some other limitations, but by law. This is most important. And I will be talking about the attacks and defense method to deep neural network. And then third part is something about personal data security, which is especially interesting, especially limited, especially, for instance, in Europe, in the United States. That's very, very important point for any project you are trying to develop, you are put in practice. So part number one is just about our work, but not everything will be here, but just part which is related directly to medical images. Normally I'm doing this collage to give a general impression of what kind of images we are using, what kind of problems we are trying to, and we are trying to solve, and we are solving them, etc. So let's start with the part number one, which is point A, and I will show you what we are doing with the so-called radiological images. Radiological images, there are a lot of them, but typically we understand that behind that term, that we mean X-ray images and computer tomography, and computer tomography is the term which denotes X-ray tomography. So that's some piece of our work, which is available, by the way, in our website. So you can put image and you can get the result. And this is a preliminary diagnosis of lung disease and some associated pathologies. You can try that, and you see on the left the original image, and then you see the heat map on the right. Is it right? Yes, it is. On the right, with some regions which are highlighted in certain scale, color scale, etc. And you can play with it if you want by yourself from any device, because it's web-based. The second, so that's the previous one is typically used for screening purposes, which is going on long time in our city, at least. So millions of images are already examined, and according to the regulations, every person living in city of the Minsk at least once a year should be examined on that. But if something going wrong, so that's very preliminary, that's the screening purpose, just preliminary analysis. And if something suspicious to be disease or something pathological changes, then typically they send people, potential patients, to hospital, and they doing CT, computer tomography scans, and that's etc. That kind of things. And we are also develop software which is doing this analysis automatically. It's concentrated on lungs. As you are specialists on this domain, you understand that first of all we need to do segmentation of lung, because that's our object, and then go deeply to understand whether everything is okay or not. So a lot of things already done here, and just a little bit to cheer up ourselves. So we show that we are currently in one of the worldwide competition on COVID-19 automatic lesion detection. On the left, you see the work which is done by a radiologist. And on the right, you see the what our software doing. And I'm proud to say that we are in the top 10 in the world, actually. And we are with the United States, with China, with Germany, with Luxembourg, and Belarus in the list. So I'm proud about that we are in the list, all of us. So that's another example what we are doing with this computer tomography. It's related to lung tuberculosis. It's happened to be that there's some caverns, some cavities appeared during the disease course, and then it is important what is inside of that. So sometimes it's very dangerous, sometimes it's not dangerous, and person considered to be completely healthy. He is not in hospital, but one day it may just be broken inside the lung, and then person can die. And our goal is to have a surgery data. We have partners in Georgia who doing surgery, open the chest and taking these cavities and looking inside, so what is inside. So the matter which is inside is saying a lot about whether it's dangerous or not. So, but surgery of lung is something very dangerous by itself. So we want to minimize that, to guess what is inside by CT images. And we have this original data about that cavities, which are just taken out of the body of patients. And then because the data are limited, we're using generative neural networks to make that artificial samples, and that sort of intelligence augmentation, if you want, or this is something else. We will be talking a little bit about that later on. So that's our another website. This is not website, this is a portal of the project. We are participate in, sorry. And this is a quite large resource with different sub-sites, etc., etc. And this is it's deployed on sorry, deployed in Amazon cloud. So if you have spare time, just go there and see, explore what is there. And so it's already about 20 countries members of this project. So that's also about our work, and this is about histopathology. Histopathology is remained gold standard for cancer diagnosis in all the countries, including our own. On the right bottom, you see that a scanner, which is a very recent one, which is installed in our center of oncology center, near to Academy of Sciences located. And this is very expensive, very nice machine, which is doing so-called whole slide scanning. And that's another application what we are doing, what we have done actually. It's solving the problem of automation of diagnosis and ranging of the danger in prostate cancer in men. This is just screen. I did yesterday, sorry. Just screen of our site. And that we arrived to the part number 2, which is about attacks to deep neural networks and related issues. So there are different ways to improve the security of data. Medical data, image data is very highly secure data. So they are very personal data, and no one wants to, because it's medical data contains what is inside of the body, and no one typically wants to show what is inside of his body, whatever it is. So that's really secure. And there's another point is that typically when we identify, we are talking about identification of person, then we are talking about face. So face recognition is face recognition for 20 years already, the cool topic, etc. But it's I just want to remind you that it's also possible to identify person, but what is by image, what is inside the body, by medical image, that also works. So that's the point. So in brief, what is the attack? You perhaps very well know about that, but nevertheless, I want to remind that adversarial attack is something, what is some kind of modification of original images, which force deep neural network to make a wrong decision. And that's very dangerous. So in our case, it's norm pathology, could be just mixed, etc. Yeah. And that's classical examples. The very, very first example, that's attack, which is a so-called gradient attack. On the left, you see panda, and then magnified. On the middle, you see magnified specific noise. This is not just Gaussian noise or something like that. That's very special noise. And then it's added with very low magnitude. You can't see, typically can't see the difference, but nevertheless, it's recognized totally different. So it's not panda, it's another object, another animal. And we're doing some in-depth analysis of this problem of attacks and defense method to deep neural networks. And here on this slide, I'm not going to go through in detail, but that shows what kind of medical images, how many. It's about 1 million we are using in our experiment. Certainly, clearly, that takes a lot of computational expenses. And this is a very simple example, very visible. So if my mouse is here, it's not here. Okay, anyway. The first row, that's original images of aorta. Aorta is a blood vessel, which is the largest one, which is near to heart. The second row, that's the magnitude of 0.02, and it successfully attacks the image. So it says the aorta is, I suppose here, aorta is pathological, what is not true. So it's pushed to wrong decision. And on the third row, you see the images with magnitude of adversarial, it's called adversarial noise, very high, but nevertheless, it's recognized correctly. So that means the problem is complicated. It's not that straightforward. The more you give noise adversarial, the stronger, the higher the probability of wrong classification of your original image. Okay, that's a couple of examples. First row, it's some X-ray of chest X-ray of a man, a young man. You see the young man. And then on the right, it's an attacking image. It's with adversarial noise, which is only recognized as pathological. So that guy is completely healthy, but then the neural network, which is very well trained with very good quality, nevertheless, it's push it to wrong. What is wrong? On the second row, you see very typical samples of histopathology images of breast cancer and hematoxylina as in this colorizing system, what is a little bit too deep to discuss here. On the left, you see that's the really cancer. You see the cells are enlarged and they are definitely not healthy. On the right, you see the same image, which is modified, which is wrongly recognized as norm, what is, again. So we did research, certain research on the, the attacks could be white box when we have all the information about the attacking system you want to attack is available. This could be black box attack, you know nothing about what you are attacking. In this case, what kind of architecture of artificial neural network you are attacking. Or maybe I'm speaking too fast. Okay, anyway, so that's a picture shows in details different kind of attacks, black box and white box for 5 different neural network architectures. And this, of course, depends on images also. Different kind of images, some of them more resistant to attack, some of them more weak, etc. This is also very important practical question. So previous pictures were about the gradient attacks, gradient noise. Gradient is really, so if you guess, that's really coming from gradient, which is in neural network. So when we're doing training, we're looking for minima of certain function. That's exactly the same gradient. And then there are different attacks, and you see most strong of them, well, the first one is which is on the second frame, is weak, which is sort of gradient attack as well, gradient sign attack in this particular case. And the last one is a Karolini-Wagner attack, which is one of the strongest, so you can't really see the difference. And then for another kind of images, histopathology images, and you see that, so perhaps you will not guess which one is malicious, which one is attack, which one is not, because the first one is just original image without any attack, but all the rest is images which attack a neural network. And another kind of images, again, with different kind of attacking.
Can we see difference visually?
Well, the whole idea behind is to make this modification so that you will not see visually. So in visual perception, you will not see that. But in fact, the noise, it's a specific noise, this attacking noise. And well, that's actually, perhaps you know about that. It's possible to do in real life, not just in images. So there are traffic signs, there are good examples, traffic signs, and they put something physically, a little bit physically modified that. It looks totally the same sign, but one says turn to the left, another one says turn to the right. So if you are moving with Tesla, then much likely it will do wrong things. So it's very practically, it's not only in medical, it's everywhere. And another case which is very common, so there was some conference and people make it in T-shirt, came in T-shirt with a certain print, certain picture. And then this visual monitoring system totally wrong, totally missed them. So they like disappear. Visually they appear, but for the system, they are not moving, there are no people. It's also possible to do. Sorry? Oh, well, I don't know. I am not specialist in the monitoring system. Perhaps they are not segmenting in real time, the face and everything else. They doing general monitoring. And also, the goal of this monitoring is not to identify people, because there's freedom. They are not signed that they should be identified. That's not allowed to identify them. But they're trying to detect, for instance, suspicious behavior. When the person, like in somewhere in Bahnhof, train station, they're moving a little bit atypically, etc. So they automatically detect it and then call to the police to physically check them, whether they're doing something wrong.
But you really believe that the people disappear? This monitoring system, if they have something?
No. I said that if you visually, as a human, as a policeman, you looking at the monitor, you see them, but the software don't see them. So that's the point. So they are not removed really from image. They exist. So you see the different kind of attacks, and then what we have done, we provide a lot of experimentation. Now, first, we attack an image with three different methods, which I mentioned before. And then we apply 3D for each occasion. In each of 3 occasions, we apply 3 different defense techniques, which actually exist. And then that's the image which is characterized the efficiency of attacking and defense of that kind of images. So without attack, it's about 93% of character recognition of disease, not disease, etc. After gradient attack, it's 60%, and then some other attack totally destroyed neural network, not physically, but it's put images to wrong class, totally. So vice versa. There's a binary, by the way, there's binary classification task here. And then we apply in different defense methods, and the last column, not last, all 3 last column shows the percentage of recognition classification accuracy after we sort of restore original images So it's better than 0, of course, like 2 last rows you see. It's still some good percentage, I would say. But it's not the original, which is 92%. Yeah, there is one even better. Sometimes this happens. Well, that's a very interesting phenomenon, but we have no time to discuss that. So magnet adversarial training, that's very easy. You have normal images and then images which are attacking neural network. On the training stage, you put them together, you train your data set on normal images and attacking images, and neural network learn something in common between them, and then you have better result than if you're just using just original images. The second, that's adversarial training, the CGD is a very sophisticated method. When you add some to the neural network, you put not only images, but some information about classes of that image. So you put additional information, then it's learn better the results. And then the last one is magnet. It's a very simple one, which is essentially autoencoder, nothing else. So denoising by autoencoder. So similar things with different kind of images. We're going, okay. So there are some other results, and there is recently, still not published, there is a defense method which is introduced in our group. So I'm not talking today about that, but it exists. Okay, that's the publication, some chapter of book which is published by Elsevier in London in this July. In July. So it's available for buying in internet. Okay, another defense, another security things which is related to images is generative networks. So instead, the setup is very simple. Instead of using real images of real people, we can generate images and using that generated images instead of real ones, and then there are no person behind that, and that is going by law, is going differently. But what is under discussion now, whether it's very, very interesting point, but we will touch it a little bit later. So I just will show you that's nice images, nice girls, which it doesn't exist in real. So the authors, they perhaps like green eyes. Oh, there are songs about green eyes that many men consider this is nice, even beautiful. So, but in our case, we are looking to specific high quality things, which are really high quality. So that's the recent technology can do that. And another example, that's if you are looking to design of your new flat, new house, then you can generate different solutions, and all that house doesn't exist in reality, but it looks nice. So you can get some ideas about the color of furniture, etc., etc. So that's also practically important for some people who bought. But we are, of course, dealing with the medical again. So so far we're using 3 different kinds of generative networks. One is a classical, I would say, DC GAN. So it's 2015, something. So it's 8 years. The idea is 8 years ago appeared. And so DC, it's deep convolutional. And then on the right, you see progressive GANs. So they start with these 4x4 large pixels, and then gradually improve quality. And recently, that's something like style guns. If you are familiar with style guns, also using this technology, something like UNet, like visual attention, etc., etc. But very recently, so I'm just reading this paper, which is written by Google, DeepMind, Princeton, and Berkeley people, very famous people, and they say that everything what you on generated images, it's somehow remind you about original one, so you can go back and trace the person and identify what actually I am not agreed with this. but we will see later. It's a really complicated problem, and it's a very deep problem. Well, in deep learning, everything is deep by definition. So that's typical, yeah. What I'm asking people to find, whether some images are real or some of them are generated, and typically from audience, people asking, have you showed this to doctors? I'm saying, yes, we do. And doctors are not very good in classification, whether it's real, whether artificial. And these very famous people, by the way, the first author of this paper is called Extracting Training Data from Diffusion Models. So the number one is Nicholas Carlini from Google. Nicholas Carlini, that's who invented this Carlini-Wagner. So Wagner, another person from Germany, and they improved this type of attack, which is really, really strong. So that guy also did some optimization for training neural networks. That's very famous. So it's not easy to recognize, doctors not recognize, but software engineers doing better. That's funny, but that's true, at least in our experience. So the last part, that's more about data security. So let me remind that generative networks is just to replace the original images to generate it, and you make it sort of free of charge. So you can generate thousands of them. If you go to our website, you can generate thousands of them if you want. Well, it doesn't work properly. Just remind you, that's the version which is something like 3 years old already in web. So consider that. But you can generate X-ray images and histopathology images, artificial ones, of two classes, norm and pathology. And this is for breast cancer again. Okay. The really hot topic, this I just mentioned, is it possible to find certain fingerprints, certain signs of original images in generated? And this paper, that big guys say that classical DC guns doing better in this respect, preserve the security better than most fashionable diffusion generative model. So let me remind you what is the diffusion. So diffusion, we gradually, step by step, adding Gaussian noise, and we train neural network not to do that because it's easy to do, but how to from the next image to go to less noised image and to come up to original one. But because this is processed all the stochastic, you will never get original images unless you have very, very tiny training set. That's what we are doing now, trying to understand. So once it's done, then you just put noise, nothing else, and then gradually using your trained neural network, you restore and get an image, original image. So I put this funny example on photo of myself, and to say that it's not an original one, it's me, but another image, just to illustrate that, to make this crystal clear. So the security problem is like that, what we are doing right now. On the left, you see original images. On the right, you see generated images. We have, well, hundreds and hundreds of thousands of them. But I must note that these diffusion generators, they are very, very slow. So you need really powerful computers and GPU, etc., to do that. Otherwise, it will be trained 1 year or something like that. So, and the question is still the same. So can we find out the signs of original images? So I would say that it's not straightforward. So we cannot compare with a certain measure, because the difference could be just distortion in space. So nothing on, it could be the same like you, so I'm addressing to previous nice talk. So in terms of a general measure, it could be the same, but it's different still. And that's the key, one of the key for identification. Okay, that's another example. What I have done is just took 45,000 people So some people, I think, asking whether it's endless or whether it ends soon. So it's soon. So 45 people, every person was scanned twice. So it's 90,000 images, and the task was, the experiment was how we can identify, not by face, but by that image. And that's the images. I'm accelerating. Okay. So that's example. The second shot is this just next to original one. In this picture, that's a pair of images just labeled, but among few, say 10, 20, 30 images, you can do this visually for reasonable time. But let's see what's happened if they're like that. So on the left, you see young man. On the right, you see aged woman. And it's not easy to do. But imagine if there are 45,000 in this experimentation. So you will perhaps never do this visually. So the answer is there. Okay, feature, so it's done like content-based retrieval, and it's done in the way using image features extract by 3 different neural networks. So you see the result of the top of right recognition of the pair of the next image of the same person, depending on the top n, where top is 1, 2, 3, etc. So it's additive measure. And from the first, you see that some neural networks producing better features and some of them not. And it's different for people of different age. For instance, this plot clearly said that it's much more easy to identify young people than old ones. So old people less recognizable. Oops. And male and female also different. So it's more easy to recognize, to find a pair of images for female, for women, comparing to men. And the last what we are doing, we are looking at the new technology which is called federated learning. Federated learning is something like training neural networks with different centers together, and under condition that no one wants to share the data. That's a very typical scenario. People don't want to share data, to give them aside, to friends even, to the partners, but project even don't, and sometimes it's strictly prohibited by a local law in the country, etc. So there are serious problems behind, and what people doing and what we are trying to do right now is trying to do this, share not the data, but share the training model. It's a step-by-step sharing. It could be sharing in terms of epochs, like 10 epochs you run on your data, then you pass to another center. And the key is here is the key, is how to generalize the particular solution training of the same neural networks on different centers. That's, well, the straightforward is just to compute a mean value of weights which came from different sensors, but that's not always a good idea. So that's what I'm not talking about, but it doesn't exist still. So this is something what we are doing for mobile recognition, and this for drones, for etc. But that's for money. Previous it's just for pleasure, and that's it. Thank you.
Please give your questions.
Thank you, Vassili, for a very interesting talk. You just simply put off in one, right?
Yes, because I'm defending our conference. So if it's just one missed, then there is another person who will do it instead of Chinese. So it's a Belarusian person in this case.
You showed us annotated X-ray images and CT images. And yes, we can see from conceptually that they are look very much similar. Yeah, but have you done some formal measures of comparison of results of this like annotations done by neural network approach and done by experts. How good like this similarity between the annotation formally, not just conceptually, that I have seen that they are looking similar.
Okay, it's work which is not just 1 year work, it's something like 5 years long work. And there are very different things done, and including both. I would say here actually 2 questions. One question, whether you recognize the real and synthetic images, and we have done this with the people, with the software, etc. And by the way, software doing pretty well, and recognize well, but people, even professionals, doing pretty bad. But yes, I understand. That's one level of this problem. Another level is whether it's helpful, whether it's going well with artificial images on the prediction stage. Is it correct? Not on training, but on prediction. Whether, okay, let's say it's a pathology, this is normal. Is this the question? Yeah. So that's what prediction doing. It's actually done in very detail, and not only for that images, also for histopathology images, for different data set, different tasks, etc. It is published actually in Informatica, the world-based journal. In our institute, and typically the difference is about starting from 3% of in terms of classification accuracy, sometimes going to 4, 5%, maybe 6%. That's the difference, and that's difference not just on 1, 2, 3, 10 images. That's the difference on thousands and thousands. So it's reliable. By the way, it's funny. Sometimes people say, "Okay, I got 98%," and never say about what test set. So if 2 images in test set and just suddenly at random, all of them correctly classified, they say 100%. Guys, I got 100%. I published in paper about 100%, but on 2 images only. So of course, it's not always true. So for me, it's important how many. That's so I would say between 3 and 6% the difference in this test. It's a specific, because we were dreaming about complete replacement, totally removing real images and doing everything with artificial, and then doing that trained neural network for diagnosis. That was the goal behind. But we have these millions of that images, so we can do whatever we want. Experimentation.
You talked about this, like epsilon, your adversarial noise, like value. It's like your invention. What does it mean, adversarial noise?
Well, this is just magnitude. If you that's easy to understand. If you want to add Gaussian noise, you have certain distribution, mean value and standard deviation. So, and then you can somehow tune it, whatever you want. This is exactly the same.
So you mean that it's just Gaussian noise?
This is not Gaussian noise.
Some like process Gaussian noise.
No. Gaussian noise doesn't involved here at all. So that's gradient noise. That's taken from neural network gradients. Yeah, of course. Yeah, it's very special noise. Not just noise like ordinary we have in real. So say that's very simple. Let's suppose that the scale is the noise is scaled inside the software between 0 and 1. And then you can multiply to a certain value to increase it and put to your original images. That's it.
Okay, yeah, probably that's enough for last short question.
Very interesting presentation. I would like to ask you, it is relatively difficult to take three medical images in comparison with other wide database or so on because of the problem of privacy. So you used three models of privacy, yes, privacy presentations, as I remember. Could you tell us something about the difference between these three models? Please, when you take use slide, describe these privacy models. So what is the difference between these three models?
You mean different medical image modalities or types of medical images? Okay, I got the point. Well, it's first of all, that's a very substantial. That's first. Second, I would say it depends on which kind of noise you add in, what type of noise. If you're dealing with gradient noise, then the most strongly resist images with the texture, because texture is a lot of variation. And the most strongly affected images which are smooth. So it depends on many factors. It's not just answer yes or no, but they are definitely different and very different. So some of them very resistant, some of them not. So more resistant for that kind of noise, like gradient, once we start from that. It's a histopathology in our case, because they are more similar to texture. But if you take the image like a tree, that would be very, very resistant.
Okay, we have to move to the second presentation. Yeah, thank you very much again.
Thank you.
Thank you. The second presentation will be given by Professor Valery Starovoitov, a writer-dependent approach to offline signature verification.
Okay, need to. Okay, presentation.
So I have no at all time after the previous speaker. My name is Valery Starovoitov, and I would like to present our investigations in the topic of handwritten signature verification. So here you can see signatures presented in paper documents, and top row, this is original, real signatures, and bottom row are fake signatures. And the task is very simple. There is one signature given, and the question is that signature real or fake? Usually, when we solve this task, it is very little information, and one can use additional original signature of the same person. Usually, this number from 5 to 15. So in practice, up to now, experts perform visual comparative analysis, so the result is subjective. In informatic community, analysis methods are based on objective approach, mainly on neural networks, and second variant, calculation of some features and application any classifiers. But the problem for neural networks approach is large number of samples for training are not available usually. And also this data must be marked into two classes, genuine and fake. And in our republic, in Uzbekistan and in Russia, the first variant is mainly used up to now. So we collected several databases of original and fake signatures, and totally around 20,000 signatures were used, one half original, one half fake, and about 500 people used these signatures. So our first result, a neural network approach to this problem. We received accuracy a little bit more than 90%, but it's required training on fake signatures, which do not happen in real practice. So that is why we refused this approach. After that, we started from classical image pre-processing of the scanned signature images. And we recommended the following method. At the first step, digitizing signature with resolution of 600 dpi. After that, if we have already scanned signatures, and if the signature is binary, we go to filtering, the third step. If it is grayscale image, we transform into binary. And if it is a color, we convert into binary representation using the dominant color. Third step is filtering by mathematical morphology and median filtering. After that, we rotate the binary image using principal component analysis, scale into a fixed template, and extract contours by method of mathematical morphologies. And here you can see example. Left top, the original color image. Next, grayscale. Top right, binary image. But you can see binary image in the bottom left usually have a lot of drawbacks, and we must filter this binary image. And at the right, you can see filtered variant much better than left one. So here you can see original images and our contour representation of the fixed size. This binary contours we called template for our following recognition. And we use not skeleton as many people, but contour of this signature image. At the very beginning, we calculate LBP patterns. So this is local binary pattern, but our application is to binary representation, not to grayscale as usually used. And here our contour is represented by zeros. And for example, for pixel presented by red color, we analyzed his neighbors and calculate code for this contour pixel equal to 60C. So we calculate codes, LBP codes for every contour pixels. After that, we construct histogram of these codes and delay the first and the last bins of this histogram, and this 254 values we called LBP code of our signature contours. Also, we studied different variants of signature representation, signature made by different color, different pens, and so on. And at the left, bottom left, you can see contour representation of our signatures before feature extraction. Here you can see original signatures, histograms of LBP codes, and correlation, Pearson correlation between two codes. Oops, sorry. You can see original and fake signatures. Correlation is low enough. Here also original and fake of the same person, original correlation is low. Below, we see high correlation for LBP codes of two original signatures made by the same persons. But this is not always the case. Here you can see examples when signatures of one person has low correlation between LBP codes, and correlation is high between original and fake signatures. So this is not enough LBP code for high precision offline signature verification, and we added additional feature like local curvature for all contour pixels. So curvature is calculated as opposite value to radius. We use 5 sequential pixels of contours and calculate curvature values for every contour pixels. After that, we construct histogram of all these values using 40 bins, and normalized histogram of these values is called in our study as signature curvature code. After that, we try to recognize, to verify signature. If we have 7, for example, examples of real signatures of one person, we calculate this LBP code and curvature codes for every signature. After that, we calculate correlation, rank correlation, Spearman correlation between every 2 pairs of original signatures. So if we are given just 7 original signatures, we have 21 new patterns for learning of our classifier. And also every of these 7 signatures we compare with the given for analysis signatures. We have 7 patterns of these pairs. So we presented new feature space. Instead of common representation of object patterns, we use correlation coefficient between features of signature pairs, and we compare verified signature with real and one real with every other real. So in this table you can see this is ordinary approach, one verified pattern signature, and the number of given real for verification. In our approach, we compare n with n multiplied by n minus 1 divided by 2. So we enlarge the feature space, the number of patterns in our feature space. And we use one class support vector machine for classification as a writer-dependent classifier. So we learn the model of our SVM just on data from one class, real signatures. And after that, we analyze if our to be verified signature belong to this class or not. So we used signatures from open database Bengali. It consists 5,400 signatures presented in binary variant as binary images, and we get accuracy 81.5%, but best in published results is about 66 on this database. Why not so high percent? Because you can see 2 original signatures of the same person. It is very hard to say that they're real, not fake, for example. And we do not apply any special efforts to improve these low-quality images. On another database, which was represented by 2,640 grayscale signature images, CEDAR, we got much higher accuracy. This is 99.77%. This is just 6 errors when we use 15 original signatures for every person for training our classifier. And you can see no any error for recognition of fake signatures. Also, best result in the literature on this database, accuracy was equal 94.4%. So here you can see example of fake and original images from this database, and here 7 original images of the same person. This fake top left fake image was recognized correctly on the left plot, because we can separate its patterns from our model presented by green. On the right plot, you can see impossible to separate. So our conclusion is this top right signature is true, genuine for our investigation. Another similar example, two top images, fake and true, we correctly recognized, but visually it is very difficult to do this fast and precisely. And third example, we can see again correct recognition of fake signature on the low left plot. So my conclusion, to verify offline signature, we suggest a new universal method of pre-processing and unification of the signature image, a new description of the signature structure by histogram of LBP codes, a new description of the signature structure by histogram of local curvature values, and a new type of the feature space correlation closeness between features of signature pairs. Using this, we got only 6 classification errors, verifying all signatures from popular CEDAR database. That's all shortly. Any questions, please?
Okay, please give your questions.
The reason why you need this contour representation of the signature instead of skeleton?
Why it's better? Yeah. Contour instead of skeleton.
Contour, because when we use our signature, for example, and lines are too close, and you use skeleton, you lost some structure or shape information. Yes. We try to save as maximal as possible normally shape information, structure information from signature.
Usually people also to keep this shape information use like spline approximation of skeletons. You get information about like curvature and so on. You can compute it from spline.
Yes, but we don't need to calculate spline parameters because this is approximation in some sense. And also, if pen is thick enough and you use signature, or in there is, for example, on notebook or some planchets, you can use signature by finger. It is not very good from our opinion. We made some preliminary experiments for comparison, skeleton and contour, and we concluded that contour is more robust for structure preservation.
Yeah, of course.
Because you plan to like extend your work not just for research, but just for some agency which is interested to use it in practice. What, speaking about this accuracy, what is your like goal to get accuracy? What they accept, which accuracy they will accept from you?
Yes, I understand, but this was outside of our research, this question. So a lot of job was connected to normally signature analysis, processing, recognition, verification, and so on. and security, it was not enough time to study.
But practical agency, any practical agency, they will accept this rate. I mean, 66%, 80% for practical use. They can check it in bank, on the police or whatever.
Police experts use up to 1 month to study originality of one signature. And a week ago, I saw a TV program exactly from expert department, and they said that they use in Belarus just manual visual analysis of these signatures presented on the paper. Yes, this is another variant, another data representations, another signature description. There X, Y coordinates, pressure, and so on and so on. This is different kinds of signatures.
No more questions? No questions. Again, thank you very much. Okay, so we conclude our plenary session. Now we have almost 1 hour break, and let's meet at 1:30 in that building, in the main building, room 522, you can see in the program. So 1:30, we meet there. Have a good lunch. Thank you.